In section 7.1, we're going to define the Laplace transform. We will ultimately be using the Laplace transform and the associated inverse Laplace transform in order to solve some differential equations later in this chapter. But before doing so, we kind of have to understand what this transformation is and exactly what it's going to do for us. So we've seen kind of transformations in the past, even though we might not necessarily have focused on them or highlighted them in that context. But for example, the processes of differentiating and integrating can be thought of as transformations. Starting with the function x squared, if we differentiate it, we end up with the function 2x. Similarly, if we had instead integrated, found the antiderivative of x squared dx, we would get the function 1/3 x cubed plus c. And in that way, we could view differentiation. For example, differentiation is a transform that associates to the input x squared the output 2x. And with anti-differentiation, the transform of x squared would produce 1/3 x cubed plus c. Furthermore, differentiation and integration also possess a very important property, that being the property of linearity. Meaning that if you have a linear combination of, let's say, two functions, let's say alpha f of x plus beta g of x, where alpha and beta are constants, then essentially you can pull the constants outside and do the transform on the individual functions f and g. So we've seen in the past, but this would be essentially equal to alpha times the derivative of f of x, which we call f prime, plus then we have our beta times the derivative of g, which would be g prime. Similarly, anti-differentiation, i.e. integration, is also linear. So if you wanted to integrate a linear combination, it's simply going to be the integrals of the two functions times their respective constants added together. So differentiation and integration is linear. We're also going to see a new type of transform now called the Laplace transform that will be defined as an integral transform, and it too will end up being linear. So recall it from perhaps a calculus 3 class, but let's suppose that we have a function, let's call it f of xy, that is a function of two variables. And let's suppose that the definite integral of f with respect to one of the variables would lead to a function of the other variables. For example, if we hold y constant, so thinking of this function 2xy squared, if we hold the y constant, then we can take the antiderivative of this with respect to the x variable. You would use your standard rules. Let me maybe show this part. So this is kind of a good review. If you wanted to do the definite integral from, let's say, 1 to 2 of 2x y squared dx, if we are holding the y constant, then essentially the 2y squared may be allowed to be pulled outside of the integral. Because again, with respect to x, if we think of y as constant, they can come to the outside. This would be equal to 2y squared. The antiderivative of x is going to be x squared over 2. And then we would need to evaluate this from x equals to 1 to x equals to 2. This is going to be equal to 2y squared. We plug in the upper limit of integration for x. We subtract the lower limit of integration plugged in for x. And we get 2y squared times, this is going to be 2 squared divided by 2. That's 4 divided by 2, which is 2. Minus, this is going to be 1 divided by 2 is a half. 2 minus a half, that would give us 3 halves. And then these two cancel, and we end up with the function 3y squared. So notice by holding one of the variables constant in this function of two variables, the original function f of xy that was 2xy squared, when we integrate with respect to the x variable, the actual result we get is a function, maybe I'll call this g, of the other variable. It's a function g of y. So let's define a similar kind of integral. Let's define the definite integral from a to b of k of s of t. So this capital K function is a function of two variables. It's a function of the variable s and t times f of t dt. This, if we integrate this, so the integration is done with respect to t. So we would be thinking and holding the s variable constant, and as we just saw with this example just a moment ago, what this will ultimately lead us to is going to be some function of the variable s. In other words, the one that was held constant. So this transformation is going to transform the function little f, which is going to be our input this time, of the variable t, into a function, let's call it capital F, of the variable s. Okay? We are particularly interested in integral transforms where the interval of integration is the unbounded interval from 0 to infinity. And so if f of t is defined for t greater than or equal to 0, then the improper integral is defined as a limit. So this is something you hopefully remember from Calculus 2, but the way that you integrate with infinite limits, we call those improper integrals, is to take the limit in this case as the upper limit of integration would approach positive infinity. So you do this definite integral from 0 to b, where we assume b is finite. Once you do that integration, we then apply the limit, and that gives us the value of the improper integral should it exist. Okay. And when that integral exists, we say that the integral exists or is convergent. However, you may have seen some examples in the past where not all improper integrals converge, and if that limit does not exist for whatever reason, then we say that the transform of this thing would be divergent. Okay. We will later on, as it pertains to the Laplace transform, we will give some conditions under which these Laplace transforms will converge, in other words, will still exist, but that will be later in this section. Okay. The function ks of t that's kind of used in this integration is what's referred to as the kernel of the transformation. And by choosing a specific choice of the kernel function, if we define k of s comma t to be e to the negative st, then that produces the Laplace transform. Okay. So this is the definition of the Laplace transform. So let's give ourselves starting off with a function f. Suppose we have f of t, which is defined for t greater than or equal to 0. The Laplace transform is a transformation that to this function f of t will produce a function that's going to be of the form capital F of s. And it's defined as the integral from 0 to infinity e to the negative s of t times f of t dt, provided this integral exists. And notationally, we'll call this new function the capital version of the original, but with the s variable. So the Laplace transform of f of t is going to be capital F of s. If we had a function g of t, its Laplace transform will be denoted capital G of s. And if we had a function y of t, its Laplace transform would be denoted y of s. Let's actually do one of these together. In example 1, let's see if we can find the Laplace transform of the function 1. So here we think of f of t as just being the constant function 1. So the Laplace transform of 1, by definition, this should be equal to the integral from 0 to infinity e to the negative st times 1 dt, which is just going to be the integral from 0 to infinity of e to the negative s of t dt. This is an improper integral. Every Laplace transform will be because of the bounds from 0 to infinity. So we have to handle this as an improper integral. This is going to be the limit as b approaches infinity from 0 to infinity of e to the negative s of t dt. This integration can be done pretty straightforwardly. This is a u substitution. If we let u be the exponent, so let u be equal to negative s of t, then du is going to be negative s dt. So to do this integration, we need to have a negative s dt on the inside. So what we can do is we can account for this. We can put a negative s on the inside if we put a negative 1 over s on the outside. So let's go ahead and do that. So it's going to be equal to the limit as b approaches infinity of negative 1 over s, the integral from, be careful, we're doing a substitution here, this is from t equals to 0 to t equals to b. I'm not going to change the bounds on this. You could if you wanted to, but this would now be e to the u du, which is going to be negative 1 over s. Antiderivative of e to the u is e to the u. Don't forget to continue to write your limit on this. You still need the limit as b goes towards infinity. Negative 1 over s, this is e to the u, and it's evaluated from t equals to 0 to t equals to b. So let me back substitute. I have negative 1 over s. Remember, u is equal to negative st. And now we're going to evaluate this from t equals to 0 to b. And as I said a moment ago, don't forget, we're still need to take a limit at the end. This is going to be the limit as b approaches infinity of the following. So we have our negative 1 over s. If I plug b in for t, this is negative e to the negative sb minus e to the negative s times 0, which that's just going to end up being 0 power. So we get the following. This is going to be equal to the limit as b approaches infinity of negative 1 over s e to the negative s b minus 1. And the only thing that's left to do now is we need to take this limit. Okay? So provided s is equal to 0, which will be the case. Remember, we want t to be equal to 0. So oftentimes we'll also kind of require, within this definition for s to be greater than 0. So provided that s is greater than 0, then the limit, I'm just going to focus on the part we need to take the limit of. The limit of e to the negative sb as b approaches in positive infinity. This is the same thing as the limit as b approaches positive infinity. If you get rid of the negative sign for the e, this would be e to the s over b. And as b approaches infinity, that denominator is going to get bigger and bigger and bigger, and therefore this whole term is going to approach 0. So what we have is that in the limit, this ends up being negative 1 over s. This goes to 0. So we get 0 minus 1, which is negative 1 over s times negative 1, which simply gives us 1 over s. So after all of this, what have we found out? Well, the Laplace transform of the function 1, which is a constant function, but generally speaking, this would be a function of t. So the transforms 1 into the function of s that is given by 1 over s. Okay, and again, for that limit to exist, this was defined for s's greater than 0. If s had been negative, if s had been less than 0, then this thing would have been undefined, as that limit would have blown up towards positive infinity. But we just calculated our first Laplace transform.